Okay, Assalamu alaikum. Good evening, everyone, and welcome to our weekly gathering into our 5th annual Knowledge Without Border. This year, it's because of the pandemic, we were not able to meet face to face, but I think at the same time, it's have a lot of opportunity that we have a lot of people, they are already participating with us today, people from Libya, from Iraq, from Saudi Arabia, from UAE, from Oman, from Bahrain, from Syria, from Jordan, Lebanon, Pakistan, India, Nigeria. And it's really very exciting to see that a lot of people is joining us for this series of knowledge sharing, which is a 5th edition, is organized by Salem DMCC. With you, Dr. Maged Hanna. I am the Managing Director of Salem, and really I would like to be welcome all of you into this gathering tonight. This initiative started 5 years back, which is aimed to share knowledge. We have every year, it's almost 4 to 6 months, we have different sessions, workshops, which is we accredit the workshops also for continuous education. So at the end of the event, when you will be submitting your names, you will receive a certificate for continuous professional development units towards your professional associations. This year, we are concentrating also more into the SDG, Sustainable Development Goals. We have 10 goals we are already concentrating with. You can see them down. It's goal number 4, 5, 6, 7, 8, 9, 11, 12, 13, and 17. Why we are already concentrating in these sustainable development goals? Because sharing experience, sharing knowledge, it's what is the aim behind it? It's transferring the knowledge from the expert people to another engineering, which is, it will be aimed to be enhancing the engineering practice. This year, I'm very delighted to have a group of a very leading organization sponsoring our Knowledge Without Border initiative and the Sustainable Development Goals. We have with us B&T Architects and Engineers, a leading architecture firm in the field of architecture, design, engineering, and management. We have with us today also is WJ Middle East. They are expert groundwater and dewatering and water solution and management. And really it's this, you know, it's this organization doing a massive work in the field of dewatering, not only just as having the expertise and knowledge, but also with us one of the highest prestigious expert in the field, which is Dr. Tsobi, which is, I will give you more information about him, which is publishing hundreds of papers, sharing knowledge with everyone, enhancing the best practice in the field of the dewatering. With us also Train. Train is a leading firm in the energy efficiency with more optimization in the energy and HVAC. And next week we'll be hearing again for an interesting and exciting presentation from them. Also, we have Hollisbridge is again another firm, is again working heavily in the sustainability and water recycling and how to be more sustainable. Also, we have Levante, again, is a leading firm into the field of building materials with high quality, with sustainable materials. So again, I would like to thank all our key sponsors, main sponsors for their support that to share the knowledge with everyone. But I cannot just only acknowledge our sponsors without acknowledging as our strategic partners. which is all of them, we are working together towards having successful events for this 4 months, starting from October till February 2021. Our accreditation partner is a Project Management Institute for accrediting all our already certification, all our already professional development units. Our federation partner, the Federation of the Arab Engineers. This is a federation which is already having a lot of meeting and gathering towards all the associations from all the MENA regions. I would like to give you a thanks and appreciation from His Excellency Prof. Dr. Adel Al-Hadisi, the General Secretary, for this gathering. Also, I would like to be having my gratitude and appreciation for our academic partners, the American University in Dubai. A special thanks and appreciation from Dr. Nabil, the Dean of the School of Architecture, Art and Design. Also, I would like to have our gratitude and appreciation for all our association partners, the UAE Contractor Association, Oman Real Estate Association, and the MENA Regional Engineering Education Association. Thanks again for all our strategic partners. Just to give you a quick announcement for today's event, so please kindly mute your mics. We will have a session for Q&A at the end of the today session. So we'll have Dr. Toby, Engineer Oliver with us, and we'll have a live questions for them. So please be prepared for any kind of any challenges you face under the ground, in the field of dewatering, in tunnels, in infrastructure, in construction. We have 2 master experts today, and we will be ready that you will be answer all our questions. Also, if you are not feel comfortable to unmute your mic and you ask the question loudly, please feel free to drop your question at the chat box. I will be the moderator for today's session, so I will read all the questions for our distinguished guests with us today. Regarding the attendance, so I would like to ask everyone attending with us today to be ensure that we have the proper attendance. Please drop your full name as well as your email in the chat box. I can see some of the people attending today, just the name is mentioned iPhone. So sorry, we will not recognize the name. So please drop your full name and your email at the chat box. So it will be that it's as a possible opportunity for already networking and also as for the attendance. If you are not feeling comfortable to share your email in the chat box, please drop your email into privately in a message to me. The certificate, it will be already published within 5 days. So within 5 days, you will receive the certificate into your email. And kindly also, in the past weeks, I'm sending you a lot of several emails. So if you didn't receive the certificate from me, please kindly check your spam folder. And if you receive it or you don't receive it for any certain reasons, I will be display my contact details at the end of my introduction. So please write my number and send me WhatsApp or send me an email, and will be issued a certificate for you. Today we will be having actually the session. It's about the black art of construction dewatering. We have with us 2 distinguished speakers. We have Dr. Toby Roberts, and we have Engineer Oliver Vincent with us, as they will be presenting for us a very exciting presentation with case studies from a project, from a real challenges they face and different solutions they had been implemented. And here is really what we need today into our market is people like that kind, which is this organization. Why? Because they are not only just they are providing a solution or a services, but they are sharing knowledge, which is enhancing the engineering sector preventing a lot of defects, errors, saving time and cost. And into this, we call it is a challenging environment. Knowledge, it is a key essential, it is a power of the organization which we are concentrating in. Firstly, I would like to be introduced for you our two keynote speakers for today. With us is Dr. Toby Reports. Dr. Toby is an expert in the field of design and implementation of groundwater control system for large excavation. Me, I know Dr. Toby, I think for the past, I can't remember, it's like 10 or 12 years. And every time I sit down and listen to him, I get to learn something new and really enjoy all the discussions and all the knowledge sharing in his presentation. Dr. Toby have a mega project through Europe, Middle East, Canada, and is very well known. If you search about Dr. Toby Robert in the LinkedIn, and you can find all his paper, articles, publishing, research, and sharing knowledge in different areas. Toby is a founder member and the current chairman of the international dewatering contractor, WJ Groundwater. He have already an author and co-author more than 40 publications. And really, I like you and invite you to go and read these 40 publications and get back and start asking Dr. Toby about them and ask good questions. In construction dewatering, including Syria C750, the recent updated UK design guide for construction dewatering. Dr. Toby Robert is a fellow of the Royal Academy of Engineers and is a chartered civil engineer and a chartered geologist. Please welcome with me Dr. Toby Robert. Our next distinguished speaker for today is Mr. Oliver Vincent. Engineer Oliver Vincent is the general manager of the WJ Middle East. So he's located here from Dubai. Dr. Toby is communicating with us from UK, from England, and Oliver with us in Dubai. He have more than 10 years of experience providing client with a practical dewatering solution throughout the UAE, Qatar, and Europe. Oliver is holding a master's degree in geotechnical engineering and have a range of experience in basement, tunneling, canal dewatering. He have a lot of WG pumps, a specialist in providing turnkey over pumping and bypass services throughout the UAE. So Oliver, it's a great thing. Is Oliver is all the time is I know Oliver again is like for the past again same 10 years almost in the UAE, and I met him on several occasions, and he is a very great person. You can approach him easily, and he will be giving you a full solution for all the issues. And the project is maybe have a lot of challenges. He will be very great in sharing a knowledge with you. That's me, Dr. Maged Hanna again. Finally, again, thank you very much for listening for me for the introduction. This is my contact details. Please, you can take notice of the communication and the contact details. If you need any assistance into regard your certification or into if you want to any guidance, advising at any kind of field in project, in risk, into cost, or if you want to be connecting with also WJ, today they will be sharing with their contact details, but also if you couldn't reach them, you can keep in touch with me and I will be sending you all the contact details. Thank you very much for listening for me. With that in place, I will be handing over now to Dr. Toby and Oliver the stage to be starting the presentation.
Good afternoon, everyone. I'm speaking to you from the UK. I'm just going to get my presentation going. Right, there we go. Okay, so I'm going to be talking to you for the first half an hour or so, and I'm going to hand over to Oliver, and he's then going to hand back to me for the finish. So this first half an hour is about dewatering techniques. These are the basic methods that we use for dewatering. So that opening photograph shows a excavation. It's about 40 meters square in a river in the UK. It's for a tidal barrage. It's about 10 meters deep below the standing groundwater level. And you can see in blue those wells around there, and they're pumping out the water, which is just flowing in underneath the cofferdam. And essentially that's the process of dewatering, temporarily pumping out the groundwater that's flowing to the excavation before it actually floods the excavation. So let's just start looking through. So the first thing to consider is, why do we need to do dewatering? What's the purpose of that? So one basic reason is that construction is labor intensive, and also construction plant is essentially designed to work in the dry. On the right there, you can see a piling rig which has been flooded because the site pumping system has failed. And it's difficult to carry out those kind of activities underwater. So the first thing is, it's much cheaper to build stuff in dry conditions. So we lower the water table so we can do that. It's important to remember that it's not just keeping it dry. We also have to think about stability. If we've got an excavation in sandy soil, then dry sand will stand comfortably at 45 degrees, whereas wet sand, fine sand with a seepage face, stands more like 5 degrees, is a very poor material to found on. So stability is actually the main reason why we do dewatering, beyond simply keeping the excavation dry. So the methods that I'm going to run through are these first 4: sump pumping, Wellpoints, Deepwells, and Ejector wells. These are active methods of pumping. I'm not really going to be talking about barriers, although dewatering systems are very often working with barriers, as we saw in that opening photograph with the sheet pile cofferdam. I'm not going to talk about passive relief wells. I'm not going to talk about recharge wells, recharge lagoons, disposal and mitigation, but those are all relevant techniques. And there are other methods of dewatering: siphons, electroosmosis, which we do use. We don't use them very frequently. So again, I'm not going to cover those in this presentation. So sump pumping. So this is the basic process of you dig an excavation, it goes below the groundwater level, the water starts to flood in, and then you can put a pump in and you can pump that away. And these are some standard sump designs. The key thing about them is to try and get them to below your site dig level, so that the area that you're walking and trafficking on is dry. And you can see on the right there, we've got the concrete manhole rings and a drain feeding water to the sump system. And that's the sort of basis of it: typically trenching and a sump, all excavated to below your dig level. And that's a standard sump setup. This was actually at Heathrow Terminal 5 before the terminal was built. It's founded on gravels, The gravels were actually cut off around the perimeter and were simply sump pumping out the trapped water. So there's actually no great stability issue in this case, but you can see it's just an open trench in this case, dug to below the surface level. There's a generator running the pump, which is in the manhole rings, and the discharge is being pumped away. So you may ask yourself, well, why can't we simply sump pump everything? What prevents us from doing it? And the answer is it's the depth to which you can dig your sumps below your dig level. This shows an excavation. It's actually on Palm Island in Dubai. It's got a secant, sorry, not a secant, it's got a contiguous pile cofferdam around the outside, so the piles have gaps in them. It's excavated down about 15 meters, and you can see the sump, the 45-gallon sump there, and there's a fairly good flow coming in, and you can see it's a pretty messy condition. But they've managed to dig the sumps to that depth, and that's because the ground in Dubai at depth is slightly cemented, so it doesn't ravel in the way that I showed you in the picture of the stability. And that's allowed them to get to that depth. This is a very similar excavation, also with contiguous piles. You can see there's one well there, but there's another 10 wells around the outside of this structure, and the groundwater's been lowered. You can see it's a dry, completely stable condition. So in this case, or in the previous case, it was possible to do the excavations. It was a struggle, it was risky, there were costs involved with managing that groundwater. Here, they've spent the money on the dewatering and they've dug in the dry, so there's a cost trade-off. If in the previous picture the ground had not been cemented, it simply wouldn't have been possible to dig to that level because you would have had too much inflow and ground loss between the piles. So it's surprisingly hard to be very specific about the conditions when you can no longer sump pump and you have to switch to dewatering, and it is partly driven by economics. People like to be able to lower the water table, dig in the dry, build their structure, and then turn their dewatering system off. That's simply a more efficient way to go. So the most basic dewatering system we call a Wellpoint system. The well points are installed at relatively close centers, typically 50 mil diameter, about 6 meters deep, and they're connected up to suction pumps that can suck air and water. And these are, if you like, sumps. They're small sumps. They're installed around the perimeter of the excavation, and you run the pumps, you suck the water out of all the little sumps, and you lower the water table in advance of your excavation. That's the process of dewatering. So you can install a well point. This is a steel well point. It's just being jetted into the ground. It's a good system in sandy soils. This is on a very constrained site where it's difficult to get a drill rig in. And this can be a cost-effective way of installing. This is a slightly larger scale well point system. Here the well points are being drilled into the ground with a rotary drilling rig. You can see the well points at the bottom there that have been installed. And you can see that the rig and everything is working pretty much at the standing groundwater level. And that's what the system looks like installed. The header main, we call it, the individual well points connected up, usually with a valve so they can be trimmed. 2 duty pumps and 1 standby pump. They're super silenced pumps, so they're in boxes. And that system is now operating, and the groundwater level is being lowered. And then that's a week or two later, excavation down to formation level, blinding installed, and they've dug down 4 meters and they're starting to build the permanent structure. Here's a similar setup in the Middle East on Palm Island again. You can see here the well points, very close centers. There's quite a high flow coming directly from the sea, the other side of that sand bund. Here's that site I showed you previously where they were jetting the well points in. So this is a basement in an existing building for a private house. This is a common construction in London where people want to extend their house. They're not allowed to go up. So they build 1 or 2 basements down, and you can see you're working in a very constricted area. And this is a much larger well point system. This is for the ECLRT in Toronto. And here we have 3 stages of well points. So the issue with well points is that they operate on vacuum. The pumps suck the water up from the well points, and there's a limit to the vacuum that you can generate. And the limit at sea level is the physical limit is 10 meters. That gets you to an absolute vacuum. And the practical limit, because of efficiencies and losses in the system, is about 6 meters. And what that means is if you want to dig an excavation that's greater than 6 meters, you have to put additional stages of well points in. And that's what's happened here. They've excavated to stage 1, that's been installed. Then they've excavated down to stage 2, and then installed that, turned it on, and then got down to stage 3. And you can see they're exposing a TBM tunnel that's been driven through this station in advance. So this is in sandy soils. The header main you can see is wrapped in that orange covering, and that's because in Toronto the temperature in the winter regularly hits -20, and we need to stop the system from freezing, so we have to have lagging through the winter months. So we can solve that problem of the limitation on suction lift by putting the pump at the bottom of the well and pushing the water out, because there's no limit, there's no physical limit on pushing water. The limit is simply on the design and power of the pump. And we have these slimline electric submersible pumps that can go in a 100 millimeter well as the sort of smallest size. The economics dictate that we don't put them at closer centers as well points. These often going in at more like 10, 20, 30 meter centers. And then we have to drill them to significantly deeper below the dig level so that we have an effective screen area. We need a control cabin with the pump starters, a standby generator, and then the discharge comes up into the header main. So this is probably the most common system that we see, particularly around the Middle East. Here's an example from Tel Aviv. This is a 5-story basement for a residential development. And you can see the deep wells there, relatively widely spaced. I think there's only about 10 wells in this whole basement excavation, as the inflows were relatively slow. We've got a diaphragm wall with tiebacks, and then in black you can just see the discharge lines. This is the equipment we use to install the deep well. It's this is a 16-ton rotary drilling rig. It's a dedicated water well drilling rig. and then we use a water flush. So we have water pump and sumps, which is where the drilling mud collects. This is in London on the Thames. So here's an example of a deep well system. This is at Łódź in Poland. It's a top-down excavation to 20 meters depth. Quite a sizable excavation, 700 meters by between 50 and 130 meters. And it's in a 60-meter thick, dense sand aquifer, quite high permeability. So this is the kind of data that we look at. In addition to the watering equipment, we have piezometers, so we can monitor the groundwater level, and we have flow meters, so we can monitor the discharge flow. And nowadays, this is all automated and continuous reading, and typically online. So the piezometers, piezometer data are these colored ones. And you can see in this case, we're lowering the water table down 5, 10, about 15 meters of drawdown in this aquifer to the max dig level. And you can see the discharge flow initially peaks at just over 450 liters per second at startup. And then over time, it drops off. And that's the sort of typically what we see when we're running these systems. So this is a pretty high capacity system. And here we've got, this is run over about a year whilst the construction is going on. Actually, the flows are reducing here because there's some adjacent dewatering going on, which is starting to impact on this. So it was a top-down excavation. You can see excavation going on there, and in the bottom picture you can see the deep wells. So they had to dig down and protect the deep wells. It was quite a nice arrangement for us because it meant the well heads and everything were up on the top on the slab, and all the discharge and the power cables. But the main contractor had to be very careful in not damaging the equipment. And our design flow was about 600 liters per second. So the peak flow at 450, we had a bit in hand, and that's typical kind of margin that you might see on a deep well system. So the final system I'm going to talk about is an ejector system. An ejector system is a jet pump. We'll look at what that is in detail in a moment, but the pump sits at the bottom of the well. It's actually a jet pump which is driven by high pressure water. So we have high pressure pumps that supply it. They're primed from a tank, and then we have a high pressure main. The high pressure water gets pumped down to the pump. Then we get more water back up than we pump down, and it goes back to the recirculation tank, which fills up and then overflow to discharge. So we're essentially using the groundwater, and then as part of our pumping system, but we use high pressure pumps to drive it. And characteristically, we have two header mains, and the riser pipe typically is two riser pipes.
قالت لا قالوا لي يوم الاحد قلت لها روحي اي فقلت لها لازم تجيبي لنا فايل من مدام قايله لك تجيبي لنا فايل وهذا وش اسمه ونزقي انت الصور واحنا نسوي واقع حال بالهذا ونكتب لك نعطيك اياه. ارادت كتب دفعت بالي وهذا حتى قديمات الطيبه قديمات وهذا قديمات.
Sorry about that. For some reason, I was muted for a moment. But hopefully you can all hear me now. So this is an ejector body. This is the jet pump that goes at the bottom of the well. It's been cut in half so that we can see what's going on. And what we have is a nozzle and a venturi. The high pressure recirculating water is pumped down in the annulus between the two concentric pipes. It gets turned through 180 degrees, exits the nozzle and the venturi, and you get a suction developing at the nozzle exit, and that draws water up through this non-return valve, and then the actual well screen is out of shot to the left. That's what the ejector body actually looks like. And you can see we have two concentric pipes. So we pump water down the outside and it returns up the inside. So that's what an ejector system looks like in practice. We've got the twin header main. We've got the headworks to get into the annulus. So it's the high pressure red pipe. So we're typically running at about 700 kPa on the supply side, between 100 and 150 psi. And then the blue is the low pressure return. And the equipment that you can see up on the right there is the high pressure supply pumps and the recirculating tank. These ejectors have actually been drilled inclined through the retaining wall. So we can look at our techniques and we can actually summarize their sort of mechanical characteristics. We've got Wellpoints Deepwells ejectors. They are 6 meters, Wellpoints typically 6 meters deep, outside capacity of about 1 litre per second, and we typically install them at close centers. And we can get some vacuum assistance, which we'll talk about in a minute. Deep wells, no limit on the depth. I've got 1 to 50 litres per second. We have used bigger pumps. Spacing anything between 10 and 100 meters. We can put a vacuum on the wells on the screen, and that helps achieve the drawdown in fine soils. Ejectors, we have a practical limit of about 50 meters. Typically, we're using a sort of intermediate spacing of 2 to 15 meters. And the benefit of an ejector is that it the vacuum that it generates will pump both air and water. And we can generate a very high vacuum, and we can generate that right at the bottom of the well. So ejectors are very effective in fine soils, but they have relatively poor mechanical efficiency, so they're not very good at pumping high flows. So we can then plot that onto this graph, which is something I originally prepared when I did my PhD 30 odd years ago. So these are the two main characteristics that define choice of dewatering system. The drawdown, the amount by which we're lowering the water table. I've got that here, 0 to 20 meters. In fact, we've done many schemes with much higher drawdowns than that these days. And the permeability going from 10 to the minus 8, which is a clay, up to 10 to the minus 1, which is a virtually infinitely permeable gravel. And we then can see that the deep wells and well points work well in the sort of sandy soils in the middle. The well points are limited, a single stage to about 5 meters drawdown, and actually slightly less when the permeability is low. Two-stage well points or deep wells to 8 meters, and then typically we go for deep wells below that, although you can go to 3 stages or more. Then there's a point at which vacuum becomes beneficial and ejectors are useful, or we have to use vacuum deep wells. There comes a point below about 10 to the minus 7 where dewatering simply isn't feasible. It may not be necessary, but essentially the amount of water that you can pump out and the rate at which things happen is too slow. You still may have problems with managing pore pressures, but we can't deal with them by pumping. And then we have a high flow, high permeability limit where it becomes cheaper to cut the water off and effectively put a barrier in to restrict the flow. And that's a kind of economic choice. So that's why these limits are always slightly hazy. Of course, we can, once we've know our permeability and we know the drawdown we need, we can plot it on here, and that gives us some idea of what system we could be using. Permeability, of course, there isn't one value of permeability in the ground waiting to be measured. In this case, as in many soils, the horizontal permeability is significantly greater than the vertical permeability. So we have to think carefully about what is the appropriate permeability to put into that graph. Is it the horizontal permeability, which it would be for an open cut excavation, but perhaps if we've got some sheet piles or diaphragm wall and flow is under a cutoff, the vertical permeability may be more appropriate. Also in rock, that diagram was very much concerned with conditions in soil. Rock is often inherently stable. Its permeability is variable. The rock may be low permeability, and in this case, we've got a karst feature, which is clearly very high permeability. So the way in which we use that diagram in rock needs to be thought about carefully. I think the main point to note in the UAE particularly, the soils tend to be a mixture of sands, silty sands, and then these become cemented at depth, and we're dealing with rocks or conglomerate, and we're in this sort of intermediate permeability area. And where we're talking about rocks, where the ground is essentially stable, in effect, we can sump pump to a much greater depth than we would ever be able to in soil. So we can also look at the conditions in a country and form views about what kind of dewatering systems are appropriate. And sure enough, in the Middle East, we tend to see deep wells, well points, and sump pumping, but not ejectors to any great degree. So I'm going to finish there. I'm going to hand over to my colleague, Ollie. That's what I've been through. And Oliver is going to talk to you about decommissioning of dewatering systems.
Great, thank you very much, Toby. See if I can share my screen.
So I'll stop sharing now.
Good evening. So thank you very much, Toby. I'm going to talk to you today about decommissioning dewatering systems. It's something that interests certainly me, and it's something that's something we should all be thinking about before we start dewatering a site, how we turn off and when we turn off a dewatering system. So I'm going to talk about benefits of external and internal dewatering systems when it comes to turning them off, look at some open cut excavations, and then look at some methods of closing out internal dewatering systems, focusing mainly on deep wells. So I always like to talk to clients and say at the beginning, well, start from the end and work backwards. So when you're thinking about decommissioning a dewatering system, you want to try and think about, firstly, timing. So structural integrity is important, and waterproofing, making sure that's all in place before you turn off the dewatering system. Wanting a dry environment for the installation of reinforcement bars and waterproofing. Thinking about how much time it takes for concrete to cure. So when you've sealed your system, is the concrete got the structural strength? Compaction of engineered backfill around structures and open excavations. So I'm going to have a quick look at that. Things that we forget about when we're decommissioning dewatering systems. And then something that some people ask is, well, what happens when I turn the dewatering system off and I have water coming into my excavation? So something you might want to think about is the reversibility of the dewatering system. Can you turn it back on? Before we turn off the dewatering system, we often do recovery tests. So we'll turn off an individual well whilst the rest are remaining operational, and we'll see, well, does that well recover quickly? Does it do what we're expecting? Sometimes you have leakages through the shoring, and the common practice of the shoring contractor when he's sealing it up is to put a little black tube down the back of the ceiling and link that to our wells or a French drain. So if that's the case, you're probably going to expect water levels to cover a lot quicker. And then consultants, main contractors, designers need to think about how to accommodate temporary works into permanent works. Dewatering is typically a temporary system, but it can have an impact on the permanent structure. We like to reuse our dewatering systems for future projects. That allows us to keep our costs down. And then really we're trying to find the easiest method of sealing with the lowest risk. And that really requires the main contractor, the waterproofing contractor, and the dewatering contractor to really work together. And another input will be from the shoring. So let's have a start. So the classic is an open cut excavation. So you can approach this in two ways, or a combination is internal dewatering system versus external. So with the internal, the wells go inside, and as the excavation reduces, you would cut down those wells to try and keep them close to the excavation. The issue comes that when you come to finishing the project, you can't necessarily just turn off and flood the site. You've got to compact the ground as you go back up, and you want to do that in a controlled manner. So if you've got your wells in the inside and they've been cut down, we're probably going to have to raise them back up as you go along. If, on the other hand, the well's on the outside of the excavation, you don't have any of those sealing issues, and you're likely to pump a bit more water, and you probably need a few more wells, but it does make your life easier when it comes to the end of the project. So this is an example of a project that WJ are dewatering at the moment. This is a nice example of an open cut excavation. The main contractor here, I think, has done a fantastic job. And at the beginning of the project, we originally had all our wells around the outside. So we probably had about a third more wells on the edge. But the contractor's looking for a cost-effective solution. So we're trying to minimize our costs. So the way we've done that is bring more wells inside. So in effect, we're pumping less water, so using less fuel. So that gives a saving. When it comes to switching this system off, we've got still wells on the outside. And the idea is that we'll keep the external wells operating and try and minimize the number of internal wells operating when that ground is compacted up. And that makes the life easier for the main contractor to work. This is a photograph of the Red Line North metro station in Doha in Qatar. Here, the deep wells are located outside of the diaphragm walls to provide both internal and external drawdown. This reduced the loading on the shoring and reduced the risk of water entering anchors when they were doing the drilling and sealing. It did mean that they needed to do more monitoring on the system, and they needed to be careful what happens if the dewatering system stopped for a reason. So WJ needed to make sure that we had extra backup on this project to make sure that that was a very low risk. At the end of the project, the wells can simply just be backfilled, or you could leave them operational or have the ability to put a pump back in if any leaks happen in the future. Another example here, this is a project going on right now in Abu Dhabi. This is the Mina Zayed tunnel. Now what you'll notice here is that all the wells are on the outside of the excavation. Now these have been placed there because the actual slab of the tunnel doesn't go all the way to the shoring. There's a gap of about 1.5 meters. So the wells have been located in between that gap. And you can see they're still upstanding right to the top, and there's some walkway platforms that allow those wells to be accessed from the surface. So when the tunnel is finished, we can simply just turn off the dewatering system once they've finished, without any obstructions to the main contractor. So I want to talk now about what happens if we've got internal deep wells. So the design of the shoring will impact the way the dewatering is decommissioned. Internal dewatering certainly needs more consideration than external. So the examples I've just given are mainly external systems. So I'm going to just give you a rough diagram. And this diagram has 4 different methods. Yes, there are many other methods, but these are the main 4 that we use here in the Middle East. So starting on the left, you've got sealed within the slab. So the top left, these green round circles, they represent a secant pile wall. And then on the lower section, you've got the cross section of the site. So you can see the deep well is within the excavation. So when it comes to turning off that dewatering system, we need to close out that individual deep well within the slab. The second diagram has a sacrificial pump. Now here, when you fully excavated, you'll cut down the deep well within the excavation. The pump will still be running, and then we'll install a duct, one for the power cable and one for the discharge line. So that is usually a PVC pipe that runs from the top of the well out of the excavation. And then the slab and any waterproofing would go on top of that. At the end of the project, if the water levels don't recover quickly, you can take the pump out. But if they do recover quickly, then you leave the pump inside the well, and that will be sacrificed. The third option is one that WJ do quite a lot in the Middle East, and that's where we drill our well down the indent between the secant piles. There is also an option to do that with a diaphragm wall, which I'll discuss later. And the purpose of this is that from the very beginning of the works, the well is located outside of the slab and outside of any waterproofing. The waterproofing will be placed in front of that well at a later date. And the final method I'll discuss is passive relief. So the deep well would start life as a normal deep well with a pump inside the internal well. When you get down to final excavation level, a French drain is constructed from that well to the external shoring. And when the shoring is drilled originally, within the pile, a steel casing is placed. And that steel casing later is tapped into and provides a way of removing the water from the French drain. So let's start with some examples of sealed wells within the slab. So this is a photograph of a project in Cork in Ireland. And this shows nicely the different stages that puddle flanges are used. So here you can see a puddle flange located over the top of the deep well. Now this puddle flange has got, let's see if I can see my mouse, you've got a flange at the top, which has the ability to be bolted to, and then halfway down, you've got a little wider disc. So when that's cast into the concrete, that creates an increases the routes that water has to pass. So the chances of water coming up the annulus of the puddle flange is less. And you can see in this photograph they're forming the rebar around it. And then down here you've got a little box, and that's going to be a box out section that goes around the well. And when they pour the concrete, that will leave a box out for this well. This well will remain operational until all the slab has been cast. Once that's been finished, the well will be cut off and the top sleeve will be closed. This is a up close version. In the Middle East, we have to have a little bit more care for the water because the water here is saline. So it can be kind of 5 to 8 times more saline than seawater. In Abu Dhabi, it's not unusual to see water with 200,000 parts per million. You put your finger in the water and it comes out with salt crystals. So everything has to be a little bit more robust. So here, we've designed our puddle flanges slightly different. They're heavier duty, so they're often PN16 rated. And we've moved that middle plate down to the bottom. So that allows the puddle flange to stay standing. So particularly if they're tall puddle flanges, you don't want them falling on anyone. And it also makes it a lot easier for the waterproofing contractor to wrap his waterproofing around the puddle flange. So I just want to show you a quick breakdown of the sequence that puddle flanges are used when sealing within the slab. So here on the right, you can see a puddle flange and the waterproofing has been brought initially across. So the waterproofing is this blue dashed line that runs underneath the slab to the edge of the puddle flange. And generally the waterproofing will be brought back up the outside of the puddle flange. This flange is best suited to be within the raft. So earlier when I was talking about temporary works coming into permanent works, this is an example of that. Some contractors in the past have, instead of putting this in the raft, they've moved it below the raft. So when they seal it in concrete down here, but issues that have arisen on this is if the project is very large, let's take a large car park, 400 meters long. You can't turn off all the wells on the same day. So you start at one end and you move in one direction. What happens is the water level at the end where you've turned off might start touching the bottom of the raft. And when water rises up, it tries to follow the easiest route possible. And that might be directly along this route, along the blinding to a well that is operational. If that well, even when it's operational, has got waterproofing here, the water's likely not to go to the well, but it's probably going to try and bulge out of the waterproofing and could damage the waterproofing. So that's why we generally recommend to put it in the slab rather than below the slab. This is the next step. So once the waterproofing is put in, mass concrete is poured around. You might just be able to pick out the fine little detail here. They've put a mechanical stopper, and they've also put some water stop bar in here to stop the water coming between the waterproofing and the puddle flange up. Note that the pump is still operating at this point. And then finally, we've got to cut the well. So you remove the pump, you cut down the well screen below the top of the flange, and you would finish off your waterproofing. And then often you would put a temporary box out section around the top of the well, and you would fill it with a low permeability material, such as an epoxy resin grout. the benefit of this is that if a dewatering system goes off, the only way water can come is up through the well and not up the outside. And then finally, finishing off, often a waterproofing contractor would put, for good measure, some grouting tubes for injections at the construction joints, before finishing off the rest with mass concrete. And you can see these tubes just coming out the top of the concrete here on this example here. So that was sealed within a slab. And the next one is sacrificial pumps. So this is where we duct power cables and through the power cables and the discharge. So sorry about the photograph, it's not necessarily the best photo, but you can see the puddle flange here. I've highlighted the inside and the outside of it. Within that, you can see the deep well, and you can see the flexi hose coming up before it fixes to a PVC duct. And that takes the power cable and the discharge under the slab. And then it comes out up to the surface. So this photograph here is from ICD Brookfield, which is a 7-story basement in Dubai. So probably the deepest basement in Dubai at the moment. And that worked really, really well. So once that's all connected up, the plates, the top cap gets closed off, and it's sealed in the same manner as the last examples. So you put a box out section, make sure that's watertight with the waterproofing, and then you finish with mass concrete. The next one, which is what WJ do a lot, is sealing within the shoring. To be able to seal within the shoring and to be able to drill close to the piles, whether secant piles or diaphragm wall, you need to have a small drilling diameter. So this is where WJ make use of their rotary drilling rigs. And because a piling rig is going to struggle to get close to that pile. So we generally drill anything between 200 and 350 mil in diameter with the rotary drilling rig, whereas our piling rigs would be drilling 600 mil plus. The photo on the left, that's HSBC in Dubai. You can see the Burj Al Arab, so just in the background. And the other photos in Qatar. So this is an example where we've drilled from the surface and we've drilled down the gap between the piles. As you see, we've got that really close to that wall. So that's out of the way of the main contractor. It's not going to get in the way when it comes to excavation. And it also is really easy when it comes to sealing. This guy here is also dipping the wells, and he's just walking along the walkway around on the edge. I've given you a second example because sometimes when the secant piles are smaller in diameter, there's less of a gap to put that well. So we have to drill and we have to use smaller diameters. So instead of using an 8 or a 12-inch well, we have to use 6-inch well. So we need more of them. And also they are susceptible to kicking out. If there's any concrete that's displaced, then that might cause the well to move further into the excavation. So really looking for a good quality finish on the piles to use this technique. Once it's ready for waterproofing, the contractor would usually put up scaffolding, put steel grids across the front of it before covering it in shotcrete and gunlighting. And as you see, the well is now nicely hidden, ready for waterproofing. I think here it looks like they're using some probably bitumen-based waterproofing. So you can also use this technique when doing deep diaphragm walls. So when you're doing your diaphragm wall, you need to put a polystyrene void spacer in with the reinforcement when they've done the trench initially. And then we would come along and drill through the polystyrene to install our deep well. So this is an example of a basement in Abu Dhabi, and you can see the wells are within the diaphragm wall. And this is an up close picture of the well going through that edge. I think you just about see a bit of polystyrene still there. And again, the purpose of this is to make sealing of the wells and making sure that the basement is watertight at the end of the project. Final method is passive relief and French drains to shoring wells. So these are some example photographs. A few of them aren't the clearest of photos, but hopefully I can explain. So the first photo on the left is a series of seeking piles. And when they've installed the seeking pile, they've also added a steel tube. You can see that that's placed within the concrete. So that capping beam, this will be cut down, the capping beam will be put in, and then this will be cut down and opened up once we're ready to put the pump inside. Whilst this isn't in use, there'll be deep wells within the excavation. So this second one is a photograph of a deep well within the basement. We've reached the full drawdown, and now an excavator is digging a trench from the deep well to the shoring. And the shoring is where this steel pipe is located. We'll then put a French drain, slotted pipe, which will then backfill with gravel. Sometimes we use a geotextile if we're worried about the soil moving. And we'll operate the external well. So you can see on the right-hand side, the well located within the shoring. And again, the benefit of this is that when they come to doing the slab, the waterproofing, there aren't any wells within the excavation. And this the well works under passive relief. So it just bleeds out the top and it goes along the side. This is best suited to low permeability soils where the flows are relatively low. The trench, I'm generally trying to get 1 to 2 degree incline towards the well to make sure it flows. So to finish my presentation, it's a question. And the question is, what will the groundwater level be when the dewatering is switched off? When turning off a dewatering system, it's common practice to carry out uplift calculations. This takes the uplift pressure from the water pushing upwards and compares it to the mass of the structure bearing downwards to check that it doesn't float, pop or crack. However, what standing water level do you take for this uplift calculation? Do you take the water level from the site investigation, which was done before the project? Often the site investigation isn't actually a monitoring well, it's just someone saying I've struck water at this level. When you've struck water, often it will rise up higher. Particularly in developing areas, there's often the neighbouring site that's been dewatered. That's going to have an effect on your water level. So taking the water level before you start could be risky. And now many areas around the world are seeing groundwater levels rising. So the range of reasons for that, increased irrigation, increased effect of damming from basement construction, precipitation levels increasing. I mean, in Dubai right now, they're doing lots of cloud seeding to try and encourage and to get more water to reduce the desalination requirement. I mean, just as the summer's reducing here, I'll be out ready for my barbecue, but then it rains. So all these things are changing. So we've got to take that into consideration when we are thinking about when to turn our dewatering system off. And also the consultants and the designers need to think about what's the water level going to be in 5 years, 50 years and 100 years time in the design life of that project. And then what's the impact if water comes into the excavation? Flooding, it doesn't necessarily need to be visible. It can be humidity, it can be dampness. You can see in this middle photograph here, this is where water's coming into a tunnel and it's causing delamination, it's causing structural damage. So these all things need to be considered. And then finally, if it doesn't work out, there's always an option for permanent dewatering, and we're always there to help. So that finishes off my presentation. Thank you very much.
Okay, thank you very much, Dr. Toby and Oliver. I think now we'll be having a 5 minutes for a break. So we can utilize this time for having our coffee, our tea, or also if you want to chat for anyone into the people in the room, you can already have a chat and networking. So 5 minutes and we'll get back to continue the rest of the presentation. Stay alert and tuned with us.
Ollie, do you want to stop sharing?
Yep.
Okay, I think we ought to be getting going now. So this final session of the afternoon, I'm going to be talking around about dewatering techniques for tunnels. This is a photograph of a couple of the TBM tunnels for the Crossrail project in London. That finished a few years ago. The line's about to be opened. The TBM drives themselves don't require any dewatering. They can tunnel underground okay. But the shafts in the foreground here that is used to launch them do require dewatering in this case. But what I'm actually going to be doing is talking about dewatering underground. So when we start looking at dewatering underground, we basically have this decision. Are we going to do the depressurization or the dewatering from the surface, or are we going to do it from in the tunnel? Often these tunnels might be in a congested urban area, so surface access can be problematic. If the tunnel's deep and we're just trying to target a thin sand horizon, then that's not so easy from the surface. The wells are relatively inefficient because we've got to drill a long way to get down to the tunnel horizon with perhaps only a short length of active screen. And just because of the depth, we're typically going to be talking about using ejectors or deep wells with submersible pumps. If we can go in tunnel, we might have better access to the ground that we're targeting because we're right at the level where that we're trying to dewater. We can do probe drilling to identify the sand or the layers that we're trying to deal with if there's some uncertainty about the ground, and I'll show you a couple of examples of that. We can use relatively short wells because again we're at the depth we need to be already. And because of the shallow depth, we can also use vacuum systems, which are often a bit easier and cheaper to run in a tunnel. So we at WJ have essentially had a sort of 30-year journey from the 1990s, when essentially we were using surface equipment underground, often quite large drilling rigs, so difficult to get them underground, and sort of standard well point equipment. And we've had various projects, mostly in London, but more recently in Toronto. You can see Crossrail in the middle. Tideway is a current deep sewage project in London, where we're now using specialist equipment that we've developed for use underground, and particularly techniques for sprayed concrete lined tunnels. So the two tunnels on the right-hand side in Toronto and Tideway, they're both sprayed concrete lined. So you require stable ground for that because essentially the face is open when you're excavating. So these are some examples of the situations where you might need it. So this is Farringdon Station in London. The TBM tunnel was driven through the station, and then the station was enlarged to form the tunnel was enlarged to form the platforms. So on the right, you can see the enlargement, and there's a sand horizon just below tunnel axis level. And we've got a Wellpoint system on the left there that's targeting that sand horizon. It's difficult to maintain the plumbing through the enlargement, you can see on the right, and in fact the well points also get lost as the enlargement goes through. So we were having to install some behind us as through the enlarged tunnel. Actually, both of the case studies I'm going to present later on concern cross passages, So quite a common arrangement for both road and rail tunnels is the tunnel. Two tunnels are driven by TBM, and then there are cross passages at intervals, and these are for safety reasons and for firefighting, so people can essentially get from one tunnel to another. And those cross passages are typically either conventional heading or sprayed concrete lining, but either way it's open face tunneling, and they need dry conditions, and we need techniques for installing wells out of tunnels to do that. Certainly the development of sprayed concrete lining, which certainly came into widespread use in the sort of late 1990s in the UK, we've seen around the world, allows you to build tunnels of a whole variety of different shapes. So particularly pedestrian tunnels coming down, connecting to the surface, and the stations themselves, in this case, where you're the caverns here are about 18 meters wide, and they're constructed in sequence. That's why you can see the sort of apple core in the middle is left. You have two tunnels on either side first, and then you take the core out of the middle, and that's just to provide stability. But this tunnel is basically taking place, it's the clay in the roof, and the invert is entirely in sand. And there's a dewatering system, actually partly from the surface and partly from the tunnel, you can see on either side. This is a compact ejector pumping station in one of the Crossrail tunnels in London. So we just built this to be small, to go into a tunnel environment. The Wellpoint equipment is actually pretty standard equipment. We've changed the plumbing a lot, but the actual pumps are much the same. Electric, of course. And we also have these high air capacity, low water capacity pumps. Very often for in-tunnel dewatering, you're dealing with low flows, but you need a high vacuum, and you might be running a lot of well points. Where you're in sort of high flow ground, almost certainly you're going to have to do the dewatering from the surface. It's difficult to handle high flows in a tunnel environment. And the drilling equipment is probably where there's most development. Top left is a rig that has some reach. They're drilling a well point out of the roof of a tunnel, target a sand layer above access level. There's a modified piling rig, mini piling rig on the right, working in some of these narrow SCL tunnels when they're opening up for a cavern. So this is very high but relatively narrow. You can see there are various wells being put in as that's come down. You can see the header mains right at the top and further down. And then bottom left is a new electric rig, which we've just had for a few months. And that works well in a tunnel environment, has the great benefit of being quiet, as well as very powerful and compact. So it's not battery driven, it has a power lead that it connects to. We also need to be able to monitor the pressure, and again we can do that from the surface, but actually you really want to know what the pressure is when you're down in the tunnel, and you perhaps want to alarm it. On the right you can see there's a piezometer being installed that's not properly sealed, and you can see there's a water pressure there of at least a bar, and risk of ground loss. It's clearly not going to be telling you a useful water level with that going on. On the left, this is a piezometer. It's actually through the wall of a basement, or a deep basement rather than a tunnel. But you can see there the sort of main components, a stub grouted into the basement wall. Then we've drilled a piezometer through that, and then bolted a flange onto the top of that. That's all sealed, and we've got a transducer and a data logger and various valves and things, so we can open it up and see what's going on. So we need those monitoring systems as well. So what I'm going to do now is actually go through a couple of case studies for in-tunnel dewatering. The first one actually dates back about 20 years. It's a relatively unusual one, and the second one, more conventional, is a lot more recent. So both of these case studies are in London. This is a Docklands Light Railway. It's a tunnel under the Thames to Greenwich. There were twin tunnels constructed. There's just a section through one of them, and the second one running parallel to it. And the cross passage we're talking about is in the middle of the river, about 27 meters below high water level, and it's just a short cross passage linking the two tunnels. Plan A was constructed under compressed air. So the contractor put a couple of bulkheads into the tunnel. You can pressurize the tunnel until it has the same pressure as the water level, and at that point you can open up the side of the tunnel, and the air pressure in the tunnel will hold the water back. That's a kind of old tunneling technique which you don't see used so much these days because of the health and safety issues associated with it, but it is occasionally used. In this case, they pressurized it. They put the tunnel under 3 bar of pressure, and during the test, up at the land side where the ground was relatively shallow, there must have been quite a bad leak from the tunnel, and that loosened the ground around the tunnel, and that blew the top off the tunnel, left a big hole in the ground, and the tunnel promptly flooded. So their plan to construct the cross passage was no longer viable. So looking at that in plan, that's the River Thames in the middle, the blowout in red at the top, the cross passage you can see in the Thames with the twin tunnels. There's a third tunnel there. This is an old pedestrian tunnel constructed in the 1920s, and it was in fact constructed under compressed air. It's a small tunnel. It's still, you can still walk through it. It's only about sort of 2.5 meters diameter. So the tunnel on the left, as a result of the blowout, was flooded, and that needed to be repaired. So on the left there, that's the roof of the tunnel exposed in a cofferdam, because they had to expose it so they could pump out the tunnel and repair the damage to the tunnel. So you've got the recovery cofferdam dewatering, which you can see is being undertaken with ejectors, because we're working in quite a fine sand in this case. So that was quite an interesting scheme, but essentially a conventional surface scheme. So this was the situation on the project. The cross passage itself, you can see the sequence. You've got the river, you've got river gravels, then about 4 meters of clay, then something like almost 15 meters of this Thanet sand. It's a very dense, uniform, fine sand, and that's underlain by chalk rock. Chalk is a very pure white limestone, but relatively permeable. actually more permeable than the Thanet sand. Prior to the blowout, the project was about 3 months ahead of program. The cross passage was the last item to be completed, last civils item to be completed prior to handover for the fitting out of the tunnels. For obvious reasons, they weren't keen to proceed with compressed air. Probably the solution which this most lends itself to would have been a ground freezing solution, but that required access to both tunnels. And that meant they had to complete the repair cofferdam, pump out the tunnel before they could start building the cross passage. And that meant the project then was going to be at least 6 months behind schedule. That was a major cost implication. So the cross passage itself, you can see, is being constructed in the middle of the Thanet sand. So you're working in this uniform fine sand. Although the cross passage sort of is a conventional tunnel, you have big collars at either side to stiffen the main tunnel. You have a catch pit in the main tunnel, and then you have a sump in the cross passage and links to the sump. So it's quite a complicated structure, and that's often the case with these cross passages. They're not simple. So the proposal in this case was actually to use a variety of solutions. So part of it was a surface well array. So there were 8 wells to be drilled into the river around the cross passage. And those were actually targeting the chalk. And this is partly a reflection of the fact that drilling wells out of the tunnel is quite a difficult thing to do when you're drilling out into uniform fine sand. And we needed to get the pressure down before we could start drilling the wells out of the tunnel. Ideally, we want the pressure down to below a bar, although we have worked at higher pressures, and you can work at higher pressures. So the wells, you can see, are cased through from the bed of the river through to the chalk, and then we actually pump from the chalk and underdrain the Thanet sand. That's a sort of established method of widely used in London of dewatering the Thanet sand. The clay above the Thanet sand keeps the water from the river out. The power for the pumps is generators on the barge with the cable. We've got a 5 meter, actually nearly 6 meter tidal range in London. So that's quite a complicated thing because we needed divers to install the pumps. So the river well's pumping about 45 litres per second. That's in total. The pumps installed by drivers from a crane barge. We actually split the power supply. 4 of the wells were pumped from a generator and 4 were pumped from a generator on shore. And then we had these in-tunnel well points drilled out of the tunnel. And there was also, as a contingency option, for compressed air at less than 1 bar. And that's another thing, I think, to think about with tunnels. You always need another, what is the next plan? If this doesn't work, what do you do next? You always need, they're almost always progressive approaches. It's very rare that you can sort of design the system and say, that's it, I know that's going to work. I don't need any contingency or backup. So there's installation of the tunnel well points. You can see on the left there, we've got a plate fixed to the tunnel wall with a valve, essentially drilling through a valve and a blowout preventer. So that stops the water and sand coming in as we're drilling. Once the well point's installed, we can seal it, and you can see the drill through valve and blowout preventer there, and the well point. It just flows because the excess pressure is higher outside, but we typically would connect them up to a vacuum system, partly so we can manage the groundwater. So the pump installation in the river, we had a crane, we've got the divers, we have a flexible riser pipe to make it easier to install in one go. And you can see we have that quite a complicated headworks with valves, flow meters, the plate that gets bolted to the pump, and then the pump riser. And that is the crane barge in the middle of the summer off to south of Canary Wharf. So some observations. So the proximity to the river above, the river wasn't a boundary condition, it was cut off by the clay, so that wasn't a concern. Under drainage of the Thanet sand by pumping from the chalk, that was something we knew about, we knew how to do that. The combined approach, that is often a characteristic of tunnel works. We needed an automated remote monitoring system, and this was the early days of those, so that was essential because they needed to know in the tunnel immediately if there was any problem with any of the surface equipment. We had program constraints with the tides, and the Soccer World Cup was going on at the same time in France, which made life complicated because none of the divers would turn up if England were in a match. Fortunately, they got knocked out fairly quickly, so that wasn't a concern. And the dewatering system was installed and the cross passage was completed in 3 months. So they actually clawed back that lost time. They built it entirely from the dry tunnel. And then the last thing they had to do once they had drained the wet tunnel was just open the plates and complete the cross passage. Okay, so this last case study, this is a more recent one. This is on Crossrail, a new east-west route through central London. It's going to be called the Elizabeth Line, and I think it's due to open later next year. And this is cross passage CP6. We had a borehole that was just 10 meters away, and that showed that the tunnel horizon was in clay. But we know about this clay. This is a clay layer at the bottom of the London clay, and it contains occasional channel sands. So these might be 2 meters, anything from a meter thick up to 5 or 6 meters thick. And they tend to have one long dimension, so they literally form a channel. So they may be hundreds of meters long, but they're relatively small channel. The sump itself reached out of the clay and into what we call the lower aquifer in London. The water level was quite low in the lower aquifer, but the sump reached into the water level. So we knew we had to dewater the sump. But the tunnel itself, our expectation was that it would be in clay, although there was that thin sandy clay horizon. So this is what the cross passage looks like. It's actually constructed with SGI steel rings, bolted rings, so very conventional tunneling, essentially a timber heading. And once that is driven through, then the sump, also constructed of SGI rings, is sunk in the middle. You can see on the right. So it's just 14-meter long cross passage. So the sump itself was going to need a drawdown of just over 6 meters. So it was just too deep to do the dewatering with a Wellpoint system. So we needed ejectors for the sump. Cross passage itself is essentially the same depth as the tunnel. So the amount of drawdown, if we had any issue in the cross passage, was relatively small. So we were confident we could do that with Wellpoints. So this was the plan. What we've got is the blue lines. Those are the ejector wells, drilled from one tunnel only to target the lower sands for the sump. So we're essentially sort of forming wells almost directly underneath the sump to lower the water level. The red are essentially probe drilling. So before we tunnel, we want to be sure that the tunneling is taking place in clay. So we drill with an auger, and this is almost like a local site investigation to check that we don't have one of those sand channels around the tunnel. So we have to check above the crown and to either side, and then the yellow probes are the probes that we're drilling underneath. It looks on this section as if we're drilling through the tunnel. In fact, we're just drilling to either side of it. So that's what the ejector array looked like. You can see the stubs that we've grouted into the TBM lining and the characteristic supply and return lines from the ejector system. One of the things that you can do is very useful if the TBM tunnel has grout plugs. You can just put a drill through valve on the grout plug, use a hand drill to drill through, and if it's clay, it'll be dry. And in this case, you can see it's we've got a jet of water and sand. The tunnel, TBM tunnel itself was concrete rings, and then you can see the SGI panel there, which are the opening sets for the cross passage. So as a result of this investigation, we did know that we had an issue. Surprise. Although we were expecting clay, we had already, because of the risks, we had already had a plan and had already mobilized the pumps. So this is what the drilling operation looks like. This is upwards drilling, where actually you can see there's a well point being completed at the bottom. You can see the opening sets for the cross passage just behind. We're auger drilling, and then as the auger hits water, we get water returns. We seal the hole, we go back in with the casing, and we install a well point. As soon as the well point is installed, we have the pumps there, and we can start pumping, and we start getting the pressure down. You can see the other well point in the picture, the one down, that's dry, that's drilled into clay. So as we're drilling, we're logging what we're drilling, and we're starting to build up a picture of what the ground looks like. And what we gradually realized is that although at the borehole it was entirely clay, we had a sand channel that was probably about 30 meters wide, and was up to about 3 or 4 meters thick. So one of the TBM tunnels was almost clear of it. It was just in the crown, and the other was almost entirely in the sand. And then we've got a plan view, the eastbound tunnel at the top, westbound at the bottom. The reds are the upwards probe. The greens are the downwards probe. The blues are the ejectors for the sump. And we can also see some that we didn't install because we gradually worked out where this sand channel was. You can see there that is where it was. So it ran across at an angle, and once we targeted the center of that sand channel, got the pressure down in it, it was okay. And you can see that LW9, the borehole, is just missing the sand channel. So even though it was very close, it wasn't giving us a good indication of the conditions in the ground. And this is the monitoring data. The flow rates were very low, but you can see in black is the surface piezometer. So we've having to take the water table down from 86 to 66, almost 20 meters of drawdown. These piezometers weren't right at the cross passage, so they're reading slightly above the level in the cross passage, but we actually took it down to below the sump level. And you can see once the dewatering was decommissioned, the water pressure starts to come back up relatively slowly. So that's a construction period of around about 3.5 months, typical construction period for a cross passage. So preliminary probing through the grout plug is very useful, gives us an early warning, allowed us to mobilize the pumping plant. The pumping real-time pore pressure data, that's vital. The pore pressure reduction as you go is very important because it becomes easier to drill as the pressure reduces. You want to pump on everything as soon as it's installed. So we always have all the pumping equipment set up and ready to go. And also as you lower the pressure, that increases the quality of your logging and the data that you get back from the drilling. So that's a very valuable lesson. And the careful logging and monitoring of the boreholes was essential in this case because we were continuously updating our ground model and modifying where we were going to put wells, how long they were going to be, what angle we were going to drill at. And actually, just to sort of turn that full circle, what we're finding now is that the in-tunnel techniques that we've developed and the compact equipment and things can be useful for surface systems. This is in fact the project I showed earlier, that was the station box. There was no room at the surface to put the dewatering in externally. This is a soldier pile timber lagging wall going into is layered sand and clay, and we've got this 3-stage well point going in, and essentially we're using the same techniques that we now commonly use in tunnel, but we're using it in a surface for a surface scheme. And that completes our session for this afternoon. This is what I've just been through. So dewatering techniques for tunneling, WJ's 30-year journey. You need the launch chambers and the reception chambers is essentially conventional surface dewatering. And I've been talking about the kind of techniques you use for stations, caverns, cross passages, connection tunnels. I skipped the Kilsby tunnel because we were pushed for time, but that was a historic project. And then we had the river wells and the DLR cross passage, and then the more recent probe drilling with ejectors and well points, and finally using in-tunnel techniques for surface works. So thank you very much for your attention to that, and we'd be pleased to take any questions.
Thank you very much, Dr. Toby and Oliver, for the great presentation and a lot of knowledge sharing. And now we'll be open for questions. So if anyone have a question, please kindly unmute yourself and you can ask the question for Dr. Toby and he will answer you.
We don't have any written questions.
We have one. Just give it a second. Engineer Nermeen, if you can just share your question for Dr. Toby, which is you had been asked before. If you can please unmute yourself.
Hello, Dr. Majid. I have no questions regarding this subject. Maybe you have mixed between me and someone else, but I just was writing my comments regarding the subject.
Okay, because I just saw it's something about the water pressure. It's before. So yeah, maybe it's not you. Yeah, sorry.
Yeah, he was asking about when we are gonna stop the discharging of water. So I just wrote that when we have an equal pressure between the structure itself and the water table. Yeah, that's all. But I'm really thankful for this webinar. Thank you all. It's really my pleasure for having this amazing and very beneficial webinar with you guys. Thank you so much.
Thanks, Engineer Nermeen.
Thank you.
Dr. Majid, I have a question.
Yeah, go ahead, Engineer Tarek.
Yeah, good evening for everybody. Actually, I have worked before with the WJG. They were joining us in one project. I was a consultant there. It's in Dubai. Anyway, I have a question about dewatering. Now, for dewatering wells, for those wells, is it possible that when you over dewatering or there is something wrong in dewatering, it will cause like a boiling point on the excavation itself?
Certainly, if you, I mean, I guess the extreme example is if you're digging in clay and below the clay there is a sand layer. Then as the sand layer has a pressure in it, water pressure in it, then as the excavation approaches the sand layer, if the pressure is greater than the weight of the soil plug, you'll get heave, and also you'll get an inflow of sand and water, which is a sort of boiling effect. So to some extent, any time you excavate below the water table that hasn't been lowered, you're gonna run the risk of boiling conditions.
So is there any way to monitor this one or to avoid this risk in the project, especially when you are excavating in deep levels below the water table?
You basically need to have piezometers installed before you start digging, and you monitor your piezometers to make sure that the water level is below the level that you're digging. And if it's not, you do something about it before you dig. Because once it's occurred, it's difficult to solve.
Yeah, because it will flood the whole excavation, I think.
Correct.
Yeah.
And in fact, the boiling is also a sign of a sort of loss of stability.
Yeah. Okay, thank you.
Thank you. Good question.
Okay, another question is written, is there any contingency reserve considered for the unforeseen work in the work of dewatering?
Yes, there is. Any dewatering system has to have some redundancy in it. I mean, that's a very good question. The question partly is how much redundancy should you have? And that depends on what are the consequences of something going wrong. I mean, with a deep well system, if you have 10 wells you would always want to be sure that if one well failed, you still maintained the drawdown. So you would always have a sort of 10% contingency. But it also depends on how good the information you have is about the ground. If you've got good quality pump test data and a high confidence in the system, you might operate with quite small margins. But it's not uncommon to have margin on capacity of almost 100%. So the capacity of that system I showed, the one from Poland, we had a capacity of 600 litres per second. We actually pumped 450 litres per second. That's quite a common sort of 20–30% is probably around about where we would like to be.
Thank you very much, Dr. Khalid.
Can I ask a question?
Excuse me. I have another question. Is it possible to share it with them?
Okay, go ahead, Engineer Tariq, and then after that, Engineer Adnan Batah. Okay, go ahead, Engineer.
Okay. Yeah, my other question is that now for any plot, normally if we are going to excavate below the water table or deep, like 20 meters below the formation level, normally we did the boreholes for soil exploration or soil test. So sometimes the diameter of those boreholes going down deeper than the excavation. So what's the risk of those boreholes against the dewatering wells? So could those boreholes affect the pressure or the water table pressure, or those holes might leak the water table so that it may cause trouble later on while excavation?
That is a very good question and a very valid point, and certainly something that we see. So the issue is that a site investigation borehole is drilled. Strictly, it should be grouted when the borehole is finished. And if it's not grouted, essentially you've got a permeable link at depth coming up. And we've certainly seen that in excavations. I guess often it doesn't cause a problem. It's just a local wet spot that has to be dealt with. But there's no doubt that occasionally there have been disasters associated with that. And certainly on a tunneling machine, you actively don't want to do drill holes that you're going to tunnel through because the face is pressurized. You can run into problems with that. So yes, if the contractor doesn't grout up the borehole, it can cause a major problem.
Yeah, but is there any specific details for this grouting, how depth we should grout it, or any mechanism, or we should consider a specific pressure to grout them, or there is no details?
There isn't really a sort of standard, but I mean, typically you would put a tremie pipe to the bottom of the borehole and pump in a low shrinkage grout until it returns to ground level. I mean, that would be the standard way of decommissioning a borehole.
Okay, thank you.
Thank you for the question.
Welcome.
Adnan?
Yes. Good evening, Dr. Majid. How are you?
I'm doing very well. Thank you very much, Engineer Adnan.
Alhamdulillah. Mr. Robert, there is some type of clay soil which is expanded when it's come wet. In this regard, what is the impact of this kind of soil on the watering system? And the second question, what is the precaution and the preferred system of the watering in case of this kind of clay soil existing in the ground?
So clays typically are too low permeability to dewater. So the clays would typically have a permeability of less than about 10⁻⁷ meters per second. so we can't actually reduce the pore pressure in them. With these sort of very soft clays, the risk is that if you drain the soil underneath them, then they may start to consolidate and cause surface settlement. So actually, when you have sensitive soils, you by and large want to avoid lowering the water level. And what that usually means is that if you have to lower the water level, then you would recharge. You would put in a cut-off wall and you'd recharge the water you pumped outside to maintain the pressure underneath those soft soils. Does that answer your question?
Yeah, thank you. In this case, do you prefer to provide like geotextile filtration?
I mean, in effect, we didn't really talk about well screens, but the abstraction well screen, we typically use a slotted screen and a filter sand. We tend to find that works better than a geotextile.
Mm. And the sedimentation tank will be well monitored for this fine soil, right?
Well, yeah, but you always want to be pumping clean water with a dewatering system, literally crystal clear. If you're pumping fines, then you're opening voids in the ground, and that's going to cause problems down the line. So yes, you do need to keep an eye on the discharge tank, but it should be clean water.
Is there any measures or features to monitor the this fine and cavity may be created below the ground other than the sedimentation tank?
There are other techniques that you can use. The thing is, even if you're pumping a really quite small quantity, if the flows are high and you're pumping for a long period, the potential ground loss is significant. So there are techniques where you pass a small amount of water through a filter and build up a sample over time. But I can't really overemphasize how important it is that the water that you're pumping should be crystal clear. And actually a sedimentation tank is a very effective way of keeping an eye on that. If the sedimentation tank is filling up, then you've got a problem with your wells and you need to probably reinstall them with a finer screen.
Mm-hmm. Thank you. Thank you very much.
Thank you. Good question. Thank you.
I have one more question.
Okay, go ahead.
Very good.
Yeah, my question that sometimes we have large developments, let's say a compound of towers or a group of towers with a large area, and those towers are connected with let's say a one basement or a common basement for all these series of towers. So sometimes we have those towers in phases. So we build one tower, and later on, after 2-3 months, let's say, we start the next phase, the next phase, the next phase. So for sure, if we are using dewatering in that development, can we make the dewatering also in phases, so we can, once we reach the weight of the structure exceeds the buoyancy force of that phase, can we stop the dewatering for that phase and continue in series or whatever as per the area?
I mean, it's a good question, and in theory, if you know the particular structure is complete and it can take the pressure, you can turn the dewatering off in that area. The thing that you have to think about very carefully is, particularly if it's a common basement, is whether water could flow at the interface between the basement and the ground if you've got a slightly more permeable layer there. So you allow the pressure to come up remotely, but then that pressure can flow along that interface. And that's what I would be cautious of. Now, obviously, if you had separate basements with perimeter walls, that wouldn't be a problem. But with a common basement, I would be very cautious about that strategy. I mean, you could monitor it, but if it went wrong, it would probably go wrong quite quickly.
Okay, so we have to maintain maybe we can switch off the wells that where we have completed the structure, but we can keep them there as a standby so that we can run them again in case of seepage on this interface line.
Yes, I mean, that would be possible. I mean, you could also possibly just put in a shallow sort of cut-off trench under the slab to kind of isolate a section to stop. You know, if you dug down, if you had a kind of 2 or 3 meter deep wall, that might be sufficient just to isolate that area.
Okay. Okay. Thank you.
Thank you.
Okay. The floor open for anyone have more questions.